Uh, Before the class, I would like to remind you some importance we have teach in last week. Okay, so I just put the PPT here, and this is I wondering to write down some important equations which I teach in chapter 5. And so there are some working equations. So before, first, we know that we have some important, we call that is the transport, right? We have some transport theory. But what kind of the transport theory? We call that the Reynolds transport theory. So if you as you remember, maybe Reynolds transport theory can be written down by the d and the dt, right? And we have some property. I use the capital B is the property we call that is the extensive property. So we have the extensive property change with the time, but we should define which domain we discuss with the extensive property. So first domain we call that is the closed. So we have the closed system. Okay, so the extensive property changes with the time and located at the closed system. Okay. And that will equal to we pick up the control volumes. So we have the control volume. The CV is our control volumes, and we do the integrations along the just located on the control volume. So what we this is a control volume should also change with the time. So we have the dt outside, and we do the integrations located at the control volumes. So what kind of the property we need to integrate? We have the small b, okay, and multiply the density inside the control volumes, and we do the integration along the all the volumes in the control volume domains. So as you can see, the B here, we call that is the intensive property. Okay, so right now we have the capital B, we call that is extensive, but the small b, we call that intensive property. Okay. So we do the integrations with the B and rho and dV, integrate along the control volumes and change with the time. So we have the outside d and dt. And then we plus another domain, we call that the control surface. Control surface is the area. And we still have the B, and we have the velocity factors and the dot product with the areas. So there is the factor, not the scalar. So we have the dot product compute in the inside integrations, and we still have the rho. Right? So we have the additional density here. Okay, and so this is the equation we call that is the Reynolds transport theory. Okay, and as we know that we call that the extensive if divided with the mass. And we will have the intensive property. And sometimes we when we discuss with the intensive properties, so what's the intensive property? Such as we can call that the B maybe is the density. Okay, why the density we call that is the intensive property? Because the density do not change it when the mass changes. Okay, because the density do not changes when the mass changes. So some properties, if didn't change when the mass changes, we call that the intensive property. Okay, so and in here we assume the capital B, the extensive property, equal to the mass. Okay, that indicates the small b will equal to 1. So you put the assumptions and go back to the Reynolds transpose series, and you will have the equations. The d and the mass, I use the small m, and the dt, and this is, we call that the closed systems. So the mass changes with the time inside the closed systems will equal to the d and dt. We integrate the control volumes, and the small b here is 1. So inside we only have the density and the d and small volume changes, and the plus, okay, along the control surface, but inside we have a rho and the v factor dot product with the small cross-section area factors. Okay, so this is the equations. We just put the extensive property inside the Reynolds transpose theory. Okay, and the second assumptions, this is our first assumptions, and the second assumptions, we consider the mass is satisfied the conservations. Okay, the mass satisfy the mass conservations. Okay, let's indicate the items I show in here. This item, the mass inside the closed system is always equal to, changing with the time is always equal to 0. So that based on these mass conservations, we actually know that the d and dt and in the closed system will equal 0. So the equation can rewrite into, we only have the d and dt and do the integration rho and dv plus the along the control surface and rho v factor dot product with the cross-section area factor will equal 0. Okay, and that's the equation I show in here. We call that the continuity equation. Okay, and sometimes we always say that it's a 连续方程. Okay, so this is a very important equations in the following class. When we discuss with the extensive property is mass, and we assume the mass is conservations because the mass cannot exchange along the closed system boundary. So all the mass survive in the closed system, and then we can call that the mass didn't change with the time. And we have the continuity equation. Okay, and sometimes you can plot. Maybe this is there is my control volumes. So the inside, the yellow, the inside here is my control volumes. And the boundary along the yellow line, is the control service, which we call that is CS. Okay? So as we see that we can have some exchanges, the mass exchanges along the control surface. So if I assume we have a left-hand side, there is an inflow, and I have the right-hand side, I have the outflow, and the area factors at the right-hand side, the normal factor is going to right? But the inflow side, the area normal factor is go to left. So if you go back to see the control surface, integrate along the control surface, we have a rho and a V and the dot product with the cross-section area. Okay, so on the right-hand side, I only have one outflow and one inflow. So I can rewrite the integration to be the N rate outflow minus the N rate inflow. Why I put the minus here? As you can see, in the inflow side, the normal factor's direction is opposite with the flow directions. So when you do the dot product, we will have the additional minus here. But for the outflow side, you see the normal factor is parallel to the flow directions. So the mass flow rate here is the positive. Okay, so for the integration along the control surface, this part, we always use the outflow minus the inflow. It's because the normal factor of the cross-section area is parallel or opposite to the inflow or outflow directions. Okay, and then for these questions, we can also rewrite the continuity equation to be the d and dt, and we call that is mcv, and plus the m rate outflow minus the m rate inflow, and will equal to 0. Okay, so you can also rewrite the continuity equation to be this formula. Okay, that indicates the inside the mass, inside the control volumes change with the time, plus the outflow rate, and minus the inflow rate is always equal 0. Okay, so the slide I just summarized which we teach in the last class. The most important thing is the Reynolds transpose theory. And when we put the extensive property to be the mass, and we can have and assume the mass is a conservation, so we will have the continuity equation in these chapters. So in the following chapter, for the chapter 6 and chapter 7, in that chapter we will replace the different properties for the capital B here. For example, for the chapter 6, we put the momentum inside the nano transpose theory. So that the capital B here will change to the momentum for the chapter 6. And the chapter 7, we will put the energy in the capital B here. And you will have a different Reynolds transpose theory formula. Okay, So the different chapter, we will put the different property and we will discuss how different they are. So in the chapter 5 here, we discuss with the mass, okay? And in the following, we will change the different properties for the nanotransport theory, okay? So we can see the table summarize all the equations I derived before on the slide. And one important thing I highlight here, this is a formula when we discuss with the pipe flow. So you can see if you discuss with the pipe flow, so how different if you consider your system is the pipe flow. So if you write down the continuity equation here, we know that the mCV dt and plus the n outflow minus the n rate inflow will equal 0. And because in the pipe flow systems, we don't have the items, the n dCV dt will equal 0. This is in the pipe flow, the NCV in the control volume system didn't change with the time. That's because this is our pipe, and because the pipe flow, there are always the water inside in the pipe flow. So the mass cannot be changed in the pipe flow. If your pipe is full with the waters, so sometimes we don't have the mass changes in the pipe flow and with the time. So we don't have this item. So the continuity equation you can rewrite to be always the n rate out will equal to the n rate in. And you see the n rate, I can rewrite to be the density out and the dense area out and the V out velocity will equal to a density in and the area in and the V in. Okay, that's the reason why when we discuss with the pipe flow and your continuity equation only have the items for the outflow mass rate and the inflow mass rate, they are equal together. Okay, so this is all the continuity equation formulas already summarized in the table, and this is an example we have done before in the last class. So this is a very simple exercise. We just pick up the controls. This is the control service boundary. Okay, and inside is our control volume, right? And the line here is our control service. So we apply the continuity equations right down in here, and we have the inflow here, and we have the one outflow here. Okay, so we actually know this is the outflow and the inflow mass rate we can compute based on the velocity or discharge. But the question we need to answer, what is the water, the rate changes is stored or just removed. Okay, that indicate we need to answer the dNCV dt is the positive. Okay, is the positive or negative, right? So we didn't know. If the dMCV dt is positive, that indicates the water is stored. If not, the negative, so that means the water will decrease. Okay, so this is the final exercise we have done before. Okay, so right now today we wondering to do many exercises and try to figure out how important of the continuity equations. So this is another equations questions we focus on the reservoir. Okay, as you can see, for here we have the inflow to the reservoir, and we have some outflow here. This is we call that the sometimes we call that the spillway, 溢洪道. Okay, so we have some water will pass through outside along the spillway, and we in these questions we have know the water level is rising on current stage. Okay, so we actually know there is a rising of the water levels. So the question right now already depicted the control service. So the dash 9 is our control service, and the inside is our control volumes. As we know, if we depict the control service already, and we know that the questions, the water is rising, okay, that indicates the inside, the water inside here is always constant, right? The water inside in the control volumes is always the constant because the water is rising. So all the blue area in here cannot be changed with the time. Okay, that's why you can see I have highlighted the equation here. Based on the continuity equation, the mCV dt is equal 0. That's because our questions, the water is always rising. When we fix the dash 9 areas, the water inside the dash 9 area always constant. Okay, so for these equations, based on the continuity equation, we only have the mass rate. This is the outflow minus sum of the control service, but the inflow rate will equal 0. Okay, but right now we only have the one inflow and the one outflow, so we can rewrite the equation to be the one inflow minus the one. I have the two outflow, right? The first outflow is contributed by the Q, the 2 here. So this is the Q2. Q2 is the discharge. And the discharge multiply the water density will equal to the mass rate. The mass rate. Another outflow is here. We have the velocity rising high is the V3, and is the velocity multiply the cross-section area will equal to discharge. Okay, and then we can multiply the density water, and we have the outflow rate caused by the rising water. Okay, and then we only have the one inflow rate. It's contributed by the Q1. And we have the density water, and finally will equal 0. Okay, finally will equal 0. So just based on this equation, you can cancel out all the water densities, and then you can rewrite the equation. So I have the Q2 plus the V3A3 and minus the Q1 will equal 0. And our target is we didn't know the rising rate. So the V3 is our unknown parameters. Okay, so we can rewrite the equation. We keep the V3 and move all the parameters to the right hand side. So the Q1 minus the Q2 and divided the A3. And then we can calculate how large the rising velocity in here. Okay. So, but if we go back to see the A3, the cross-section area A3 is equal to the 40 miles square. And I have highlight here 1 mile is equal to how much FT we have. So we first we change the dimensions. The 40 miles square multiply the 5280, and this is the 1 mile. Okay, this is 1 mile and change it to the FT, and we should have the square, right? And we can change the dimension to be the FT square. Okay, so here we know that the 40 multiplied to 5280 square, and the unit will to be the FT square. Okay, so I calculate the area first. This is the area of the water service. Okay, too big. So maybe I just leave here and we go back to see our equation. Here we have the V3 and the Q1 is the 400 and 1000. And this is, you can see the unit I showing here is a CFS. So what is a CFS? The CFS is the cubic foot per second. So it's a FT cubic and per second. This is a discharge unit. This is a discharge unit. So the CFS, we sometimes is a FT cubic per second. So in the same way, if I call that the CMS, that indicates this is meter cubic per second. Okay, the cubic meter per second. Okay, so but in here, our unit is a CFS. So this is FT cubic per second, and minus the Q2 is 250 and 1000 here, FT cubic per second, and divided the 40 multiplied 5280 square, FT square. Okay, so you can double check the unit balance, dimensional balance. Finally, your unit in here is the velocity dimension. It's the FT divided S. Okay, so you can use your calculator to check the answers in here. So I check at my side. So after I compute, the answer in here is 1.345 and 10 minus 4 powers, and this is the FT per second. Okay, but as you can see, the answer I show on the right hand side here, the dimensional I change to the hour, the FT per hour. So we know that the 1 hour equal to the 3600 seconds. Okay, so if you can multiply the answer with the 3600, and that's because we know that the we can convert the second, but the 1 hour per second. Okay, so you can rewrite the unit if you multiply the 3600 seconds. So finally, you have the 0.484 FT per hour. Okay, so this is our final answers. The water will rise in 0.48 FT per hour. Okay, so it's just this is the idea. We apply the continuity equations to the reservoir, and for the reservoir problems, we actually know we have some input flow and there is the output flow, and since we define the control surface along the water boundaries, So we still have the one outflow. So that's caused by the rising of the water surface. So totally in this problem, the two outflow involved and only one inflow we discussed. Okay? So this is a very good exercise, and we can try to practice how can we apply the continuity equation. And in the following will be a little bit complicated, the different problems. So we have the water tank. So this is the water tank, and we actually know we have the there is the water depth. So we have the water depth h, and the diameter of the tank is the 1 meter here. So maybe I write down the dt is the 1 meter. This is the diameter of the tank. It's the 1 meter. And we have the outflow. We have the outflow rate here. And the outflow pipe in here. We have the diameter. Maybe I use the DO is equal to 0.1 meter. Okay. And how the velocity here, this is the outflow velocity. So as you can see that we can apply the Bernoulli equations. As you remember, the Bernoulli equation can be applied to the same straight line. So we can pick up the 2 points, one point at the surface, another point at here, and we apply the Bernoulli equation. We will know that the velocity for the outflow side is the 2gh. So that indicates the velocity, flow velocity just depends on the how depth the water in the tank. So if the depth of the water is large, the flow out velocity is large. Okay. So for these questions, we can define our control surface boundary. So for me, I will follow the water surface. Okay. And this is my control surface. So I pick out the red yellow line is the yellow line is our control surface, and the inside is my control volumes. So that the problem is how long we need to calculate the water surface in the tank will change from the 2 meter to the 0.5 meter. So how long? So we don't have the time. We didn't know how long the time. But we know that the H0 initially is the water depth is 2 meter, but will change to the final is 0.5 meter. So we need to calculate how long the water depth can be changed from the 2 meter to the 0.5 meter. So first, you should write down the continuity equation, right? But in here, we know that the mCV dt, and we only have the one outflow, and there is no inflow. So we know that we have the outflow rate, and will equal 0. It's just based on the continuity equation, we know that the relationship follow this formula. So that indicates the first we should understand what is the mCV. Okay? How large is the mCV? So we have the if we have the area, right? The area for the tank multiply the if we have the volume of the tank and multiply the rho is the water density, and then we have the mass in the control volumes, right? So what is the volume T? The volume T will equal to the area of the water surface. So the area of the water surface is will equal to 4 over pi dt squared. This is the surface area of the water. And we know that we have the water depth. So it's water surface multiply the water depth is the total volumes of the water in the tank. Okay, and then the first item we should calculate the dN/CV dt, right? So we should calculate the n dt, and the inside is the density 4 over pi dt squared and multiply the water depth. And you can check the density is incompressible, okay? And so it's a constant, and the diameter of the tank also the constant value. So we can put all the constant value outside the differential, and the inside we only have the dt and the dh, right? That because it indicates the water depth change with the time. So, and the second items we should figure out is the mass rate for the outflow. Okay, so if we know that we have the density, and if we know that the area of the outflow, the cross-section area of the outflow, and we have the velocity of the outflow, A multiply V is equal to discharge, and the discharge multiply the density is equal to the mass flow rate. Okay, so what we have, we know that the low density and the area is also the 4 over pi d0 squared, and the V0 here is root of the 2gh, right? It's root of the 2gh. Okay, so if you have the equation 1 and the equation 2, and you can go back to the continuity equation showing here. You have the continuity equation. Okay, so you can write down the equation balance is rho w 4 over pi dt squared dh dt plus the rho w and 4 over pi d0 squared and the root of the 2gh will equal 0. And we can cancel out the same parameter is rho w and 4 over pi over 4. Okay, so finally you can rewrite the equation is I just keep the dh and the dt here, and I move all the parameter to the right hand side. So that's the minus and d0 squared divided the dt squared, and this is 2gh. Okay, and I put all the parameter at the same side. So I also rewrite, I can dh and the root h here, right? And the right hand side is also have a d0 square and the dt square, and we have a 2g here, but we have the dt, and we do the integration both sides. So we can do the integration, and we do the integration. And the left hand side, the integration interval, we know that we have the h0 depth going to the h final. And the right hand side, the integration is start from the 0 time and to the final time we have. So the answer we need to require how long is the time, is a TF here. We don't know the TF, the final times. So we can do the integration based on this formula showing here. So I do on the left hand side here. So after I do the integration, it will be the h, and this is 2/1, and multiply the 2 times. And the integrate interval is start from the 2 meter to the 0.5 meter. Okay, and the right hand side, we have the minus diameter of the outside is 0.1, and divided the diameter of the tank is the 1 meter, right? Okay, and this is I use the square, and the 2 root 2g is 2 multiplied 9.81, and multiply the TF. Okay, so you just put the water depth inside the equations. So you have the 2 times, and there is the root of 0.5 minus the root of the 2, and I can compute the constant value on the right hand side. So this is 2 times 9.81, and take a root. Okay, and then multiply the 0.1 2 times. So the right hand side, the number is minus 0.044 around 3, and the TF. So you can compute the final answer for the TF time. So the left hand side is the root 0.5, and minus the root 2, and the 2 times, and divided 0.0443. Okay, and the answer is close about to the 32 seconds. Okay, you can check from your side. I'm not going detail here. So this is also a very good questions. We just apply the continuity equations. And because after we set up the control service, and then inside the control service, we know that the volume will change. Okay, so the control volume, the mass will change with the time because the water depth will decrease when the time increase. So the problem is how long the water surface, the depth will change from the 2 meter to the 0.5 meter. So you should deal with the integration problems to calculate how long we have. Okay, so this is a very good exercise, and we know how can we apply the continuity equation. And the second exercise also very important, but right now we change the fluid topic is the gas. And we know that the gas can be compressible. Okay, so again, we depict the control surface. So we have depict the control surface here, and we have the hole. We have a small hole here, and the small hole we will have the outflow. This is a mass outflow, and the question already provide how fast the mass flow rate for the outflow. So that will equal to the 0.66, and the pressure. So you know that the pressure inside the tank, if the large, the flow rate outside will higher, and this is the cross-section area of the hole, and divided the gas constants and the temperature. And here, the question is the temperature is the constant temperature. So we know that the T in here is 33 degree plus the 273. Okay, so it will equal to 296 Kelvin. Okay, it's a constant temperatures. Okay, so and what we need to answer the questions is also the time required. But right now the time required for this case, we wondering to know if the pressure is start from the 500 kilopar to be the 400 kilopar, and how long the time required. So we know that the gas will flow outside when the time increase, and after the gas flow outside, and the pressure inside the tank will decrease. Okay, so how time required for the pressure changes? Okay, so again we just write down first. We write down the continuity equations. Okay, and here we only have the one flow out, right? And then there is no inflow. So we can rewrite the continuity equation to be the dmCV dt plus the n rate out will equal 0. Okay, so we first discuss with the mCV again. So we first discuss the mCV, and in here because we depict the control surface here as the dash line, and we know that the mCV will equal to the m shell, the tank, the mass of the tank boundary, and plus the rho is the gas is a meson here. So the rho I use the Ch4 and the volume of the tank. Okay, this is our mCV. The mCV involves the solid tank and also the gas inside the tank. Okay, so how about the mCV dt? We can rewrite to be the dm shell dt and plus the d rho Ch4 dt multiply the volume and plus I keep the rho Ch4 but the volume dt. Okay, so as you know that the shell mass cannot be changed with the time because the tank always is material is a solid, cannot be changed with the time, and the volume size also cannot be changed with the time. Okay, so how the items finally you only have the mCV and the dt will equal to the tank volumes, but the rho Ch4 dt. Why the density can be changed with the time? Because the pressure inside the tank will change with the time. And the fluid right now, our target fluid is the gas. Gas can be changed with a different density under a different pressure condition. If the fluid is the water, so the density may be not to be changed, right? So the key knowledge here, how density changes with the time. How can we represent the density change with the time? So we know that the ideal gas law, we have the ideal gas law, right? So we actually know the P will equal to the rho RT. So the density can be rewritten equal to the pressure divided the RT. Okay, so we can rewrite the equation here. The mCV dt will equal to the volumes and the d and dt, and I replace the density to be the pressure and divided the RT. And as you know, the gas constant and the temperature always constant value, did not change with the time. So we can take the outside the volumes divided the RT, and the inside we only have the pressure changes with the time. Okay, so this is the final formulas associated with the dNCV dt. dNCV dt. Okay, and the second conditions we have now the M out rate here. This is our second condition. We have the M out. So this is the M out rate here. So we can combine the equation 1 and the equation 2, and based on the continuity equation showing here, we have the continuity equation showing here. So you can write the equation to be the V divided the R and the dP dt plus the N rate out. The N rate out is 0.66, and we have the pressure, and we have the area, and divided the root of the RT will equal 0. Okay, so you can rewrite all the parameters you want. So for me, I keep the same parameter in here, and you move the outside. You move the second item to the right hand side, so you have the minus 0.66 pressure area, and divided the RT. Okay, and I keep the dP dt on the left hand side and move the all parameter to the right hand side. So you have a 6 minus 0.66, and we have a pressure and the area, and divided the total volumes of the tank. And there is the RT root in here. Because I move the RT here to the right hand side, okay, so finally it's equal to the root RT. So I wondering to deal with the integration problem, so I put the pressure together. So the dP and the pressure, I move the pressure here to the left. Okay, and the right hand side I only have the minus 0.66 A area divided the volume and the root of the RT and the dt. Then we can do the integration for this problem, and all the constants showing here. So I draw the integration in here. So how the pressure changes? The pressure changes from the 500 kilopascal to be the 400 kilopascal. Okay, and the right hand side, the time is start from 0 to the final times I need. Okay, so you can do the integration for this problem. So here I rewrite the problem. We know that the integration will equal to a long p, right? And the interval is the 500k to the 400k. And you can rewrite it will equal to the long, and inside is the 400k divided the 500k, and then will equal to the minus 0.66. The area, the small hole of the area is here. The 10, this will equal to the 10 minus 7 meters square. And how large the volumes? We have the volume is 10 cubic meter. So we have the 10 cubic meters, and the root here, the gas constant values, we have the number in here. is the 518, and the temperature we have right down in here is 296, and finally is equal to the TF. Okay, so you can use your calculator to compute how large the TF we have. And as we know that the answer on the right hand side, the bottom of the right side, is almost equal to the 1 day. So it's the 8.610 4 seconds. Because we know the 1 day, the seconds is equal to 864,000 seconds. Okay, so almost the time required 1 day, and then our pressure inside the tank can be start from the 500 kilopascal to be the 400 kilopascal. Okay, so this is also very good exercise, and we just based on the continuity equations, and we need to discuss how the volume the mass changes in the control volumes. And because our target is the gas can be compressible. So that's the reason why the density will change with the time. So we have the density change with the time items, and apply the ideal gas law. So we can write down some formula, have the pressure change with the time. OK， 那这个有点需要微积分的一些观念，所以如果你积分不太会的话，就有点抱歉。不过它的道理很简单，就是连续方程质量守恒。那你圈出来的这个边界最重要，你圈出来这个 control surface 的边界里头的 control volume 控制容积，你就要去想你要怎么去做连续方程的平衡。连续方程的平衡。好，那我们休息一下。